and welcome back for a new video on the multiple well system and specifically how we calculate capture zone for a well or a well pair or a system of wells. So just as a reminder from the last lecture, what is exactly the capture zone? That capture zone is really the space, the spatial extent, where your well is going to pump. So if you compare this to the cone of depression, right, which is what we've seen, remember those lectures on radial flow and, the zone of influence of your radius of influence of a well. Typically, we're talking about spherical contours. But of course, because there's a gradient, typically there's a gradient, on the aquifer. Now you can see that the capture and the drawdown are two different things, right? So the drawdown, can be felt up to here, for example, if the radius of influence is this much on either side. But the capture itself, right, can only be up to here because there's only so much water we can pump against the gradient. Okay, so the capture zone upstream is, all the way to the radius of influence, essentially. But downstream, right, if you have pollution in this space, even though there is a depression, right, even though there's a drawdown from the well, the bulk water is actually flowing, away from the well as opposed to inside into the well. So this is really different. Again, the cone of depression is, right, the region where there is drawdown, where you can see drawdown. The capture zone is the region that contributes the groundwater extracted by the extraction wells, right? So this is different. Like there's no water contributed from this zone because, again, the water is going away from the well, okay? Again, same illustration, but from the side view here on the top. So you can see that, down gradient, right? There's a stagnation point here where, again, downstream or, further from that point, from that stagnation point, flow is away from the well, okay? Again, if we look at top view now and you see the flow lines, right? The flow lines, these are the potentials. The flow lines are flowing into the well. So this flow line is still being curved to that stagnation point here, right? And so the extent of your, and I'm sorry about this, the extent of your capture zone here is, this distance here, and then downstream from the well, where that stagnation point is located is really important because that's really, all the way down gradient where you can actually pump water into that well. Now here are a couple of equations that we use to calculate those dimensions, if you will, or to design our wells, right? So x and y are, of course, the x and y directions. So this is the equation essentially for the flow line, right? So you can see 2 pi k b, right? This is 2 pi k b I is what we've discussed before over q. So this all comes from your, standard flow equations, essentially. Okay, kb is your transmissivity, right? Y is just y, I is your hydraulic gradient, and q is the pumping rate in the well. Okay, so yeah, this is all explained here. X0, now this is important, right? So X0 is your stagnation point, and that tells you how far it is from your well. And again, look at this. This is a pretty simple expression, right? X0 is the pumping, it's basically a ratio or a balance between the pumping of the well and the ability of the aquifer to provide water to the well. So it's transmissivity, right? Times the hydraulic gradient, right? So again, Kb is the transmissivity, and I is the hydraulic gradient, okay? Similarly, Ymax, right, is given by Q over 2kBi, so same thing, but there's a pi missing. So we can now, put this into a simple application, right? So compute the capture zone of an interceptor well, pumping at a rate of 190,000 cubic feet per day from a confined aquifer with a hydraulic conductivity of 1,500 feet per day, original hydraulic gradient 0.3%, and a saturated thickness of 75 feet. Okay, so now we have all the numbers, we just plug them in. So the stagnation point will be a little less than 90 feet from the well, right? Minus sign, so downstream. Ymax will be 280 feet, right? So again, Ymax being the maximum half width of the plume, if you will, right? So if the plume is this way, if this is your well, this is x0, and this is y max, right? So this is really the half, right? So there's a symmetric capture zone, right? So y max again is that half width essentially of 281 feet per second. And then you can you can draw those lines because now you have x as a function of y only if you replace all the constants, right? So you could draw this whole flow net, if you will. Another approach, right, are just to tie it up with the methods we've seen for Wells hydraulics so far. So all those graphic methods where you just essentially use like type curves, right, and you kind of lay the data on top of the type curves, and then that gives you information about the aquifer. Here's the same thing. So if you have a known pollution, right, and the extent of a plume, you can actually lay it on type curves, on top of type curves, or lay type curves on top of the map of the pollution, and then design well systems this way. So this is just an example, and again you can find this paper online and use examples, but we'll run through a quick example here. So essentially it's the same as before, right? Y is a function of Q over BU. U is the velocity, right? So U is the Darcy velocity. B is the depth or the thickness of the aquifer. Y and X, so it's essentially the same as before, right? So YD equals BUY over Q, and then here is the illustration of this. So again, these are just capture zone, or flow lines, I suppose. Flow lines, right, with standard distances for different ratios of Q over BU, right? So if Q over BU equals, 400 meters, 800 meters, 1200 meters, so on and so forth. So these are type curves. You can do the same thing with 2 wells, 3 wells, 4 wells, okay? So again, you can see the type curves here, and that intuitively, right, that should give you a sense that, of course, if you put more wells, then, you can get bigger capture zones, or you can have, more wells pumping the same amount, right, together. So that can also be interesting to have like several wells as opposed to just one well. And you can see here how they would, how their capture zone, changes. So if you have 4 wells, right, the thickness is just more. Okay, so here's a quick example just to illustrate this. Example designed to illustrate the use of the capture zone or the type curve, the graphic type curve, method to design a well system for a pump and treat system, right? So let's say we have this TCE plume. Again, remember the TCE is that trichloroethylene, this degreaser. That's a big problem. There's a lot of sites that are polluted with it. We did an example in the last lecture. So again, if you want to do a cleanup of this measured plume, right, how do we do this? Well, thorough investigation of the site, right, shows that the plume is like it is below. Hydrologic studies show that the aquifer is 10 meters deep. Gradient is 0.2%. We have K is 10 minus 4 meters per second. The effective porosity is 0.2, 20%. Storage coefficient, 3E minus 5. And the permissible drawdown for each well is 7 meters. Right? So the advantage of using multiple wells, right, is you can achieve the same capture zone, but not draw down as much, right? So imagine if you wanted to have just one well doing the same work, you would need a lot more pumping and a lot more drawdown at the site. So here, if we allow 7 meters, right, we can calculate how many wells do we need for this. So again, this is just a calculation, right, where B is 10, U is 3 minus 7. Excuse me, let me just clean this up a little bit for you. Okay, so B is 10, right? U is 2E minus 7. So this is hydraulic conductivity, porosity, and hydraulic gradient. There you go. Gives you U. Q now we calculate 800 BU. So 320.8, and then the drawdown is 5.7 meters. So again, this is all detailed in the original paper. Excuse me, this paper here, right? That I'll put as an activity, as an exercise to show you, how you get all these numbers. But this is basically showing you that if you have a 3-well design, then you can have a drawdown that is less than the allowable drawdown, right? It's 5.7 meters. 7 meters. So it's 5.7 meters is less. So when you have 3 wells, then it works basically. If you had 2 wells or 1 well, it wouldn't work because you'd have to pump way too much down in the aquifer. Okay, thank you very much. And in the next video, I will switch from that pump and treat systems to actually a remediation system, meaning in situ remediation. So instead of pumping out, the pollution and treating it at the surface, we're basically injecting something in the ground and hoping to develop typically bacterial or biological, essentially, cleanup solutions. So they're literally injecting the soil and maintaining the soil or the water, quality, so that to favor or to enhance or to facilitate the remediation in situ, so inside the aquifer itself. So we typically isolate and then clean. So I'll talk about this in the next video. Thank you.